says going live. You're live. And the pump outlet will fall. Got some gluing syringes. Oh, these are not the kind for taking your medicine, but yeah, for getting glue, some adhesive where it needs to go. Actually, we kind of use these around the shop here sometimes to squirt fluid in and out of different passages just to see where things connect up. And yeah, what does a syringe like this? Draw it back, suck in a charge of fluid, push it forward, eject. What does a syringe like this have in common with a piston pump? Right? It's a very similar concept. In fact, you may have seen some of our 3D videos where piston pumps are likened to a group of these syringes spinning around on an axis and sucking in some fluid and then discharging again at a different point in the rotation, right? Some people like to call the axial piston pump a swash plate pump, right? There's the swash plate, and there's the piston slipper pads at the back there. And yeah, we've kind of cut away a good chunk of the cylinder barrel here. You don't usually see so much of the piston, so we've cut away quite a bit to make it a little easier to understand what's going on. Maximum displacement, off stroke. Right, so there we go. A couple of basic concepts already coming into play there. Right? In fact, that'll be our pop quiz question today, because you've got choices, right? You could have chosen a gear pump. You could choose a vane pump for your hydraulic machine, perhaps a few other variations on that. So why use a piston pump? What's the main advantage, or what's one of the key advantages of using a variable displacement axial piston pump? That'll be our pop quiz. Why use a swash plate type of pump? Hello, this is Carl from lunchboxsessions.com. Welcome. Let's have some fun today with axial piston pumps, variable displacement pumps, and we'll also spend some time making adjustments to the pressure compensator and the maximum volume stop, sometimes called Qmax. And as always, let's keep in mind the power and the force behind hydraulics. Potentially injurious and lethal force is there. So what we do today in our short hour together is not to be considered as comprehensive training for making pump or live power unit adjustments. Make sure that you take the training required in your jurisdiction from whatever institute is necessary to certify you for work on hydraulic systems, and follow all precautions necessary to keep yourself safe from the hazards of hydraulic systems. On our lunchboxsessions.com/live page, you'll notice that there are some data sheets for you to download, and those data sheets cover off on the 3 main hydraulic pumps that we'll be working with today. Over here behind me is a Nachi America pump. There's an oil gear and also a Bosch Rexroth. So whether we have time to open those particular files or not, I don't know. But for you, if you're interested in the exact pump models that we worked with during our time today, those data sheets are there for you to download and explore more of the specifics that go with those pumps. our humble thanks to you for all of the wonderful messages that you've sent since our last YouTube Live. So many of you sent in encouraging emails and messages by LinkedIn and left remarks also on our YouTube. That's fantastic. Thank you very much for that. Just slowly getting used to, after this is our fourth now, I guess, and so I'm slowly getting used to our live broadcasts, and it's just great to be with you again today. Welcome from Bulgaria, Turkey, Indonesia, somebody here from planet Earth apparently on the list, Saudi Arabia, Bahrain, Holland, and that's Tool Time Chris over there in Netherlands, thank you. Canada, Poland, Morocco, India, Philippines, the UK, South Africa just joined in. Thanks for joining us today. Yeah, it's fun for us to be able to share during this time our 20 plus years of working directly in heavy industry and the things we've learned in hydraulics, and I hope our time together is of benefit to you as well. You'll probably notice that there is a live chat where you can interact with us, and if you're not already aware, you'll have to be logged in to your YouTube account or other Google services in order to be able to use that live chat and send us questions during the broadcast. Feel free to do that, and we'll do our best. If your questions during the chat have to do with the content of today's presentation, we'll do our best to get to those. If you have other questions about our services, other questions about hydraulics, what have you, feel free to email us, info@lunchboxsessions.com. And also another great way to interact is to find me on LinkedIn, Carl Dyke, Industrial Teacher. I should be pretty easy to track down. Send me an invitation to link, and we can also chat back and forth that way. I enjoy that a lot too. Sometimes I get a little bit behind in some of my interactions with you, but keep reminding me, and I'm sure over time I'll catch up. I do enjoy chatting about hydraulics and your various mechanical maintenance issues wherever you are on planet Earth. Okay, this is our fourth live broadcast in a series of 8. There'll be 2 more in June. The next one is on particle contamination. There's one near the end of June on servo valves and servo cylinders with Temposonics in them and what have you. So we'll do that one in late June. And then there's 2 more also, one more in July, one more in August. Keep track of our schedule and our topics at lunchboxsessions.com/live. Okay, a shout out to my great friends at fluidpowerworld.com. Fluid Power World is your resource on components. It's a great place to go to learn about machinery design and the latest in system engineering. Keep track also at the events link on Fluid Power World. There were scheduled for this year some live conferences. Perhaps that's gotten a little more complicated, but keep up with the events tab there, and there may well be a virtual hydraulics conference across the fall, and we'll see how that goes. I'd love to meet you at the conference. Great learning opportunities and great opportunities for us to interact. Today's session is sponsored by Oil Gear. For nearly 100 years, Oil Gear has been engineering industrial products for extremely challenging environments, from the depths of subsea work to moon exploration. Pulp mill bale presses, steering pumps on mining haul trucks, and many other heavy-duty continuous run applications feature the reliability of Oil Gear engineering. Welcome also to Brazil and Russia and Mexico. Thanks for joining us today. All right, so as we get underway talking about piston pumps and specifically a couple of the adjustments that show up quite commonly on a pump controller, as you know, I often like to show you some of the photographs from installations that we've encountered in our travels. So a collection of photos over the years from various different industries that we come and go from. You'll probably recognize this particular pump as a Rexroth A10 series, and what you notice, of course, is that there appears to be 2 adjustments. Hoping everyone can see my little white magnifying glass there highlighting various controls. And of course, if that second controller out from the pump body has no control hose hooked up to it, an external control hose that would come back, then in all likelihood you've only got the single adjustment of pressure compensate. And this one here, often the load sense, or sometimes referred to as flow compensator, has been tightened right down and knocked out of the control scheme, and there's only a pressure compensator. Uh-oh, I think there's a pump controller under there somewhere. Some pumps get a little bit dirty in operating environments. Here's another. So we're looking from the shaft end, but if we look towards the cap end of the pump, we'll see a cylindrical protrusion off to one side. Yeah, sometimes it sticks out off to the side, and we can see an adjustment there. Single adjustment, pressure compensator, and we'll have to look in a moment to see what does it mean to adjust a pressure compensator. Here's another style, oil gear with transverse types of controllers across the top of the pump body, and that's another way of arranging. And you can see a couple of adjustments, one on one side sticking out and one from the other. Okay, so a couple of adjustments there, and we'll get into those and what they mean in a moment. Here again, it's fairly simple pressure compensated piston pump with a single adjustment pointed towards the shaft end. Okay, what do we got here? Mobile equipment, some Caterpillar equipment. I believe this one's from a grader. And again, we see the two controllers sticking outside of the pump body. Pressure compensator being the larger one, or pressure cutoff. We're going to talk about that. That's limiting a maximum system pressure, watching out for that very tippy top pressure. Yes, there may be a relief valve set another 300 psi, perhaps higher, but that's for just in case. This pressure compensator will be the main top pressure regulator. Here is that load sense or flow compensating. That won't be the topic of today's. That'll be for later in August when we come back to look at load sense. And if you're interested in margin pressure, low standby pressure, those types of things, join us in August for that one. But you may have that control hose coming in, and so you will have to look into your machinery maintenance and adjustment notes to find out what it is you need to do to knock out the effect of the lower flow compensator, load sense compensator, in order to allow you to adjust the pressure compensator. Or join us in August and we'll cover that one at that point. Here we are again, basic Rexroth A10 type of installation with nothing hooked up to the load sense, so just often shipped together as a package and only single pressure compensator in action in that particular scenario. All right, so let's move on and start thinking about what is inside of a piston pump. So a few movies from our website here. Let me bring up the first one. Let me just pause, and I'm just going to go back to the beginning there. All right, so I mentioned syringes before. There they are, spinning between the spokes of a bicycle wheel. I guess we made the world's simplest pump. And you can see those syringes drawing back on the inlet side, drawing in oil through the larger kidney and the valve plate, sucking in a charge, but then due to the angle of the swash plate, those syringes push forward again and eject hydraulic oil out on the outlet, and hence the need for that angled swash plate so that we can understand how it is that the syringes, maybe they're pistons actually in reality, but how those syringes draw in a charge of fluid and push back out again and eject fluid. Okay, but really it's not so much about syringes, but let's think about that device called the swash plate. Here's a simple one where we've left the handle in play. Not very common to have a handle. Oh yeah, okay, so what we've done there is change the angle to half. So now our pumping rate is slower because our pistons only draw back so far and only discharge. Oh, hey, what happened there? I think our swash plate went to the perfectly vertical position, and now our pistons no longer draw in fluid, nor do they eject fluid. One could say that the pump is off stroke, okay? And yet the rotating group is still spinning if there is a shaft from a prime mover. So that's a fairly basic idea of what piston pumping action is all about. We've got additional clips on our lunchboxsessions.com if you want to see more of that. Okay, and now let's do a little bit of thinking here about what's happening in the piston pump adjustments that we want to speak about. If you come to a condition in a hydraulic system where the cylinder loading or perhaps the hydraulic motors are overloaded, or perhaps we're in a condition where directional valves have closed and blocked the primary flow of pump fluid through the system. Any of those conditions basically are an example of an overload condition where the pressure would run away to much too high a level. And traditionally, of course, with a gear pump or a vane pump, one would rely on the relief valve to take all of the pump's flow back to tank, but would do so at a top pressure value. And there's some disadvantages to that. We'll get to that in a minute. Enter the piston pump, which allows us to have a controller for that swash plate and say, hey, if we get to the point where the system pressure is too high, perhaps we could just reduce the flow from the pump to near zero and then hold the outlet pressure with just a tiny tip back on stroke of that swash plate and be ready for a time when the directional valves open once again, be ready for a time when the hydraulic cylinder isn't overloaded, and then the pump could come back on stroke automatically. And that's one of the jobs that is covered off by the pump's pressure compensator. So here we go. Let's have a look at the scenario where on the outlet of our pump, we've got a pressure gauge, then a needle valve, just so that we can shut in the pump's flow. For most of you, that will just be the moment when your directional valves close. You could also think of it as a moment, though, also when your hydraulic cylinders or perhaps your hydraulic motors are overloaded. So we'll close in the needle valve. We'll see our flow meter drop to zero beyond that needle valve, and we'll see our pump's maximum pressure value come to a high value as that needle valve is closed. And let's see what happens. Our pump has gone to a zero stroke condition. It's already off stroke. Well, how was that achieved? Okay, so perhaps a little out of sequence, but let's think about it. It's very hard to demonstrate it perfectly in that a lot of these things happen almost instantaneously, certainly within a small fraction of a second. So if we cut open to that pressure compensator that we saw in some of my photographs as we were getting underway, what we will see is a very small spool, only the diameter of a pencil, working against a fairly stiff spring that was adjusted by you, if you're the maintenance technician, to a certain pressure. And what's happening is pump's outlet pressure is available, and as the pressure gets high enough, also acting on the end through a drilled out, bored out passage, in this case, driving the spool towards the spring and uncovering a passage that drops down into the control piston. And you'll see that control piston again from the side in just a moment. And perhaps we exaggerate and move that pressure compensate spool a little too far compared to how much motion it actually is under, but allows you to appreciate the action of what that pressure comp spool is up to. What it is doing is working. Here we go. Let's increase our pressure here. Let's talk about that a little bit. So if we dial that Allen key clockwise, we come up to a higher pressure, and what can we say has happened? Well, it's just made it a little bit more difficult for that pump outlet pressure to shift that spool against that stiffer spring, and now our outlet pressure on the pump will come to even a higher level before the control piston that you see here, the large control piston, de-strokes the pump towards zero. And anytime that pump gets to that zero angle, due to internal leakage in the pump, that pressure will start to fall a little bit. Then the spring in the compensator will close up the pressure compensator once again, and a device called a bias spring or a bias piston down at the bottom in this pump will try to drive that swash plate back on stroke. There's a bias to this basic pressure compensated pump that says, hey, I'd like to go back on stroke to full production if I could. Okay, so that's the spring there at the bottom, which in this case also includes a piston. There we are, back on stroke. It's not a very steep angle. The large majority of pressure compensated piston pumps don't tip that swash plate too far past 20 degrees. There's the odd one at up to 22 degrees. Some very heavy duty pumps, this angle is only as much as 15 degrees. So it doesn't look like all that much when you see through from the side. Okay, a couple of other adjustments that you may or may not have on your pump. This one is called the maximum volume stop, sometimes referred to as Q maximum. Q, a common letter for describing flow rate. And this one is adjusted when the flow has an easy, unrestricted path through your system, no pressure loading. And if we dial that hex key clockwise, basically what will happen is we prevent that pump swash plate from ever reaching that 20-degree angle. Perhaps we're now at only 17 degrees angle or 15 degrees angle. And perhaps if we keep turning that hex key a little bit further, perhaps we could reduce this pump, here we go, to only half of its original size. Perhaps now we are pumping only at half of the gallons per minute that the pump would be at when that maximum volume stop, Qmax, had been backed all the way out. Again, that particular adjustment is made when there is a full flow path for oil from your piston pump throughout the hydraulic system with very little to no restriction at all. Okay, so a basic introduction to a couple of adjustments that are commonly made with pressure compensated pumps. You may have on your pump an additional adjustment, but called the minimum volume stop, and we'll talk about that one a little bit later on. All right, let's think a bit more about the adjustments by working with some simulations in the fixed and variable displacement pumps session on Lunchbox Sessions, scrolling down past the lessons and the videos, some exciting new videos that we'll catch up with later in our session. And let's go down to our key simulations where you can practice making adjustments to piston pumps in a cutaway scenario. So as that simulation opens up, what you will notice, of course, is that we're looking at the cylinder barrel in cutaway form, and you must use your imagination to understand that the cylinder barrel with its pistons is still spinning, even though you're looking at the cutaway in 2D where that's not as easy to show. So looking over to the left here, you see a bit of a 3D mimic that we've left there to remind you that the shaft is still turning, the prime mover is still running, and that cylinder barrel is still spinning. So, given that reality, given the fact that, in this case we don't have a bias piston, many pumps are situated like this where there's only a bias spring, and that bias spring tries to always push that pump to the maximum displacement by getting that swash plate to the maximum angle, whatever it happens to be. And you'll see as I'm hovering over various components in this pump that if you look to the symbol in the upper right corner of the screen, some of those components are also lighting up to help you understand how to read the schematic symbol. All right, so our pump is on full stroke. It's displacing according to a flow meter further down here on the right on the pump's outlet line. We're displacing 10 gallons per minute. Our pump swash plate is at its maximum angle. And it says that our outlet pressure is a mere 100 psi pressure. That doesn't sound like too much to me for a hydraulic system. And if I said, hey, maybe our pump pressure compensator shouldn't be at that level, or perhaps there should be a different pressure, perhaps set it to 700. And if I went over here to the controls on the right-hand side of the screen and I started moving them around, and perhaps someone would argue that now I'm set to, here, let's set it to around 750, somewhere close to that. There we are, set at 750. You might say, hey, how do you know that? Well, in this case, only magic text here above the simulation, so that's not realistic. As you know, anytime you make an adjustment to a pressure control in a hydraulic system, a pressure gauge should have followed your every move. And in this case, our outlet pressure didn't change at all. We were not in the right system state for changing the value of the pressure compensator, were we? What state do we need to be in to adjust the pressure compensator? That's right. We need to have our flow out from the outlet of the pump blinded out in order to take that pump into the condition of triggering that pressure compensator. Okay, so here's that pressure compensator, that little spool. Okay, and the pressure, let's just be clear that the servo pressure that operates the control piston to de-stroke the pump, that comes from the pump's outlet. And pump manufacturers have a variety of clever ways of taking that outlet pressure through some passages, often in the cap end of the pump, and routing it up into that pressure compensator to make it available so that when the compensator shifts, you'll have a source of pressure to fill up a control piston, a hydraulic cylinder of a sort, in order to de-stroke that pump. So yes, we were not in the right state for making adjustments to the pressure compensator. If you make a few turns with a wrench and a gauge doesn't follow you, probably something wrong with your procedure or something went wrong with the control. Put it back. So keep track of how many wrench turns that was for safety's sake. Let's put it back and start back to where we were. And now very carefully, we're going to close in and blind out the flow of the pump. I'm just closing in the needle valve over on the right-hand side of the screen. For many of you, that will just be returning your directional valves into the neutral state and making sure that they stay there if they are blocked P-port directional valves, as they commonly are with the use of a pressure compensated pump. So there we are. Our system is blinded, and our pump's flow has been blinded out. You'll notice that our flow meter indicates we've dropped down to 0 flow rate, and now we see our pressure gauge, and if it's a very fine resolution pressure gauge, we might see a tiny variance if we could detect it, and that might be due to what the pump swash plate is up to and other points of internal leakage. On most pressure gauges, you would not see the needle moving at all. All right, so if we want to make an adjustment, if 500 psi is not the correct maximum pressure setting to support functions of the hydraulic system, if the manufacturer of the hydraulic system require perhaps that it be set at 750, we now simply need to very carefully turn, and now our pressure gauge should be following our every turn of the wrench, and it most certainly is. The pressure on the pump's outlet gauge is following the turns of the wrench. That's a good sign. Perhaps we were supposed to be set at 750 psi, and we've arrived at that point. And what you see the pump doing, what happens? What really changes as we dial up that pressure compensator setting? We merely increase the tension of a spring, making it a little harder to move that spool, waiting for a little bit more of a buildup in the outlet pressure before that device triggers and starts to move the pump off stroke. Does it change a lot what you see the swash plate doing when you are in the cutoff position? Pressure cutoff, by the way, is another PCO, is another typical three-letter acronym that often shows up for the pressure compensate function. POR, pressure override. It seems like everything in hydraulics has 3 names. I didn't make up any of them. They are what we read when we read various different machinery manuals from different manufacturers. But make sure you understand the definitions of those types of terms for the machine you're working on as per the manufacturer's manual. All right, what changes simply is that the bias spring is allowed to try and get those pistons to punch just a little harder against that outlet oil when it takes a little bit higher pressure to trigger that compensator due to the higher tension on the spring. Doesn't change the action of the swash plate all that much. As you know, hydraulic fluid is not that compressible. It is, slightly, but pretty hard to detect a change in the swash plate position just by dialing that spring. It's very subtle. All right, so we're set to 750 psi, and we're in the right state for having made that adjustment. If we want to make that other adjustment that we were going to cover in today's session, which is the maximum volume stop, that one's down here. And you can see right now that the maximum volume stop, a threaded rod coming in through the center of our control piston, it's not even touching. So probably this is not a good time to adjust what the maximum volume. Here, I'll play around with it. Why would we do this? Why would we try to adjust the maximum volume stop when clearly you can see the threaded rod doesn't touch the control piston? Clearly nothing is changing on the output flow meter. So we must be in the wrong state for this adjustment. System state. The state we need for our hydraulic system is to have a free and easy flow path. So I'm going to open that needle valve back up, and away we go. Our flow meter registers once again the maximum flow possible for this pump due to very low restriction to the system. Perhaps we're circulating right back to tank, perhaps only through a return filter, not sure. Okay, it's off to the right somewhere, the rest of the system. But now we see our swash plate is sitting with the control piston against that threaded rod, the maximum volume stop. And now is a good time to make that adjustment. Perhaps 10 gallons per minute is going to spin a hydraulic motor too fast. Perhaps that hydraulic motor is turning a fan on a system for cooling liquids, hydraulic oil, engine coolant, who knows. And perhaps the spin rate of that fan motor will be too high. Or perhaps this pump is oversized for future expansion, and right now, perhaps it's only supposed to run at 8 gallons a minute. You will need a flow meter. Okay? This is where pressure gauges don't help you much. You need a flow meter in place so that yellow-black object in this case is one style of a flow meter that might be in use. And what I have done by adjusting that maximum volume stop, usually clockwise on most pumps to reduce the volume setting, okay? But check your pump data sheets to find out which direction to turn, and if possible, read the manufacturer's instructions to find out how much reduction in flow you should expect for every quarter turn or full turn, and learn about your pumps. Data sheets are so important. Okay, so we're altering the flow rate of the pump, but that has no impact on the maximum pressure. Nothing noticeable for the function we're carrying out right now. Okay, 8 gallons a minute. There you go, maximum. So we've prevented that swash plate from hitting the 20-degree angle. We've stepped it back a short amount, and we've made those two adjustments that I said we were going to make in today's session. We're just going to have a quick look at a few other simulations briefly, and then I'm going to answer the chat questions that you may have so far. So the second simulation that we're going to get into here is just to remind ourselves that in many a case, pressure compensated pump on the outlet in many cases often will still include a relief valve. Okay, there's the odd symbol that, there's the odd hydraulic system that we encounter does not have the relief valve teed in to the pump's outlet line right near the pump's outlet port, but the vast majority of them do. And in many a case, that relief valve is there in case of a system pressure spike coming back against the pump. The relief valve is typically the faster acting device. The pump takes just a little bit it all happens in a fraction of a second, but the relief valve may be faster. And then some also argue that due to the small diameter of a compensator spool, that it is perhaps the easier device to get stuck with contaminants. And so then the relief valve is perhaps a backup. Begs the question as to how much redundancy one might need then in that case. But if you have the relief valve there, then the manufacturer of the pump, or perhaps the manufacturer of the hydraulic system overall, will specify that that relief valve has to be set higher than the pump's pressure compensator. And typically those ranges for the relief valve higher than the pump's pressure compensator can run anywhere from 150 psi higher all the way up to 400 psi higher than the setting of the pump's compensator. Okay, there's a number of ways to approach this, but for the uninitiated and for those who want to be most careful with this process, if you are quite sure that relief valve and pressure compensator have been moved out of the original setting, might be to make the beginning adjustments or to make the beginning of this process with the power unit shut off. So I'm going to shut down that pump, and I'm going to turn the pressure compensator all the way and tighten that spring up so that the compensator will not react. The relief valve, I'm going to make sure that it's all the way backed out to its lowest possible setting. So when we start up, and we'll assume that we're going to start up against blocked P ports in your directional valves, that would be common. And so I'm going to close my needle valve to simulate the idea that you're working with a closed center hydraulic system. P ports at your directional valves are blocked. okay, which may very well be the case. So my relief valve is backed out, my pressure compensator is tightened down, and now when I start up my pump once again, follow all of the lockout procedures that you must use in your jurisdiction, of course. We're moving quickly through simple simulations. At this point, all of our flow is over the relief valve, which means we really don't have a variable displacement pump. We don't have pressure compensated function right now. Remember, we tightened down that compensator all the way. Okay, so let's turn that relief valve setting to the required value. You'd find that in your machinery manufacturer's adjustment notes, perhaps on the schematic. That's where we like to find that. In this case, we'll say the relief valve is supposed to be set perhaps to 1200. Notice that a pressure gauge is following my every move, so therefore my process for adjustment is working, it's correct. You are only setting a system relief valve when all of the pump's flow is passing through that relief. So we're set at 1200, and without wasting too much time, one now wants to get the wrench, the hex key on that compensator, and start backing it down, because, as you know, oil over the relief valve for any prolonged period of time is going to cause some serious heating. So moving over to the compensator and turning counterclockwise, in this case it might take a few turns before the system starts to react and the pressure gauge starts to keep up with your every wrench turn counterclockwise. And so perhaps in this case, we'll say our pressure compensator was supposed to be set 200 psi lower than the relief valve, and now we have that setting. We know that our relief valve is 200 psi higher than what's on the pump's pressure compensator. Another really good thing for us to notice before we move off of the simulations, which we'll do shortly, is to notice the case drain line. The case drain line is not optional on a piston pump. It is that critical third hose that is always there, and draining the case is so important because there is internal leakage. There are a number of clearances where there may be small amounts of leakage passing between parts, but also important to remember that if the compensator is active, if that spool is shuttling back and forth, and yes, we move that spool farther than it does in reality, helps us understand its directional functioning, what you will notice is that there's actually what one could argue is controller exhaust, a small amount of fluid with every punch back and forth that needs to be drained out of that active device. So there it is. We also notice that when the control piston gets to its maximum length, just so that we don't go past 0 degrees on the swash plate, just so that we don't crack this pump in half, there may be on the control piston a relief orifice limiting how far that control piston can travel, and you may notice a sudden surge in case drain flow as that orifice is uncovered. And so that's a reason why you may see a sudden spike in case drain flow if you're measuring it, and we'll talk about that some more in a moment. All right, so that's enough just to draw attention to the relief valve, because we won't do that live relief valve adjustment on the power units that we've got here today. We've done it in simulation form. Okay, and now one last simulation before we answer today's pop quiz answer question. And so let's just go back and look at simpler scenarios. Why such a fancy piston pump with all these controllers? Couldn't one just use a gear pump and a relief valve? Most certainly, you certainly can. But if you spend any amount of time pumping that gear pump over relief valve, which doesn't accomplish much for motion control, useful work is not happening when you're pumping over the relief valve. You're simply converting your input energy into heat. And well, there's the issue. It's a waste, right? So in this case, we have a proportional valve. The operator has the spool only approximately half open, not even, and is wanting to control the rate at which the cylinder extends. That sounds like a perfectly normal thing to do. Decide how fast I want the cylinder to extend. Well, if the valve is only half open and we have a lot more flow available from that gear pump, the remaining flow has to pass over the relief valve, because pushing against a valve spool that's only part way open builds up the pressure between the gear pump and the spool at maximum system pressure, cracks our relief valve. And so if we go over to our energy graph, on the left here, on the vertical axis, we see flow rate. We see our pump is pumping at maximum flow rate. And because our relief valve is open, we're also pumping at maximum pressure. But the yellow box is of interest because that's our flow and pressure at the cylinder where our desired work is happening. And so we'll see that we're only at about half of the available flow because the operator wants the cylinder to be slow. And we'll only see that, we're only using a small fraction of the system's total pressure. Yes, the cylinder is very lightly loaded at this moment. So what about that diagonal line? Well, that diagonal line, as many of you know, that's our horsepower line, our power line, letting us know how much power does it take to move the load. Well, this green diagonal gives us an indication of how much power that is. It's a function of both the amount of flow and pressure, where our gear pump, the source of the system, with the relief valve, the length of that diagonal line for both pressure and flow is much longer. So what one can see is that the length of the dark blue line so much longer than the length of the green line. That's comparing the power required for the load versus the power required for the whole system, and hence the reason we fill in that blue area with lots of red. That is wasted energy input, whereas if we were running with a compensated pump, let's change, look at what happens. With a compensated pump, yes, with the valve, the proportional valve only partially open, that is still going to trigger the pressure compensator, which will now put us in true variable displacement mode. We're at an operating point in the active region. This graph should look familiar to you. If you look through the data sheets for piston pumps, you will commonly see this graph with a start of a downhill slope, letting you know how much internal leakage may happen in that pump as you come up to the corner. And at the corner here where we trigger into the pressure compensator function, it falls off much more steeply. And on this steep slope called the active region, we are now with the swash plate somewhere between minimum and maximum, moving back and forth, constantly triggering as pressure drops a little bit due to internal leakage. The pump comes back on stroke as the pressure compensator closes using the bias spring until those pistons find out that yes, the directional valve, the proportional valve is still only partly open, and we quickly build up the pressure. So we are here at a constant pressure value, but at least now our pump is supplying only the flow required at the working end of the hydraulics, meaning the directional valve and cylinder. And so our blue line, our dark blue line, is not quite as long as it was when it went corner to corner. We have certainly saved a certain amount of energy. Perhaps we could beat that yet, but that's a topic for late August when we get into load sensing. All right, so to answer our pop quiz question of the day, which I think was, hey, why use one of these swash plate pumps? I think that you can see, and I see that some of you have certainly answered it there. You've got it right. This type of pump will save you some energy, for certain. Energy at both the electric level if it's an industrial plant, diesel fuel if you're working with an engine-powered prime mover perhaps. And if you save that energy, then you also kept your hydraulic system a bit cooler. All right, that's great. Let's go over to questions that you may have today and see what's happening. Andrew asks, is K-strain flow large enough that it could be a useful place to put the oil cooler? Yeah, you know, K-strain flow is usually not something that you want to interrupt. Some pump manufacturers will say, hey, that K-strain pressure going back to tank, don't let that pressure right at the pump's K-strain outlet port get any higher than perhaps 1 bar, 15 psi. Other pump manufacturers will have a different scenario where they might allow it to come all the way up to perhaps 75, 80 psi, perhaps 5 bar, but usually no. Usually that, even for I see you asked about a closed loop system. Yeah, but K-strain flow usually has to be left uninterrupted on its way back to tank, and that if additional cooling is needed, then typically another kidney loop pumping unit is involved, drawing fluid out of the tank and through a cooler for that. Great question though. Some people do put a filter on their K-strain line back to tank, and again, that's a contentious matter because it can easily bring up your K-strain pressure to a high enough level that you're interfering a little bit with the pump's pressure compensator action and also the natural migration of lubrication flows through all the working pieces inside that pump. Jalal asks, he's asking about the best adjustable. How much should be the difference between the compensator and the relief valve? Yeah, Jalal, it tends to vary from system to system. Some pump manufacturers, let's see, what are all the factors there? So the steepness of that line in the active region is a factor, as is the override value for a relief valve. So typically you want to have a little bit of separation there so that the relief valve and the pump's pressure compensator never have a moment where they might overlap and both try to react to a high pressure condition. So it tends to run the range of having the relief valve set 150 psi higher to sometimes having that relief valve set up to 400 psi higher. So check with the manufacturer of your machinery, your hydraulic system, or check with the manufacturer of the pumps that you're going to use and see what they recommend there. There is a bit of a variance out there on that topic. Arnab asks about the pump not needing an unload valve. Let me think about that. An unload valve. So an unload valve, yes, typically an unload valve, if I understand Arnab, is there to take all pressure out of the system, bring it down to very low standby. There's a number of ways to achieve that, even with piston pumps. Can be very advantageous if there is a long period of standby over top of just letting even a pressure compensated pump be de-stroked but at high pressure. So those are very advantageous, and especially for long times when there is no call for pump flow in the hydraulic system. I hope I answer that. It's not necessarily critical if the manufacturer has determined that the pump will cycle on and off and use flow on a continuous basis. Different designs. Let's see here. Tool time, Chris. Do you think it's acceptable to use a motor with no load as a flow meter? Oh, to measure shaft RPM. Well, that's clever, Chris. I think there are some flow measurement devices out there that have rotary shaft devices in them. I haven't thought of using an actual hydraulic motor. I think maybe you want to work with a hydraulic motor that has the minimum amount of internal static friction, a very high mechanical efficiency rating, I guess, where is that the right way to think of it? Anyway, you want to work with a hydraulic motor that spins very easily, perhaps so that the flow meter itself doesn't load the hydraulic system. I can't see why that wouldn't work. Very clever. Let's see here. Samer's asking, do you think for the Rexroth A10V that you have to have pressure cutoff there? And perhaps there's no need for a system relief valve. Yeah, there are certainly hydraulic systems we bump into where if the user is very confident that there will be no pressure spikes, and the user, and by that I do mean the hydraulic system engineering group, they're the ones ultimately responsible for the safe design of the system. But if they're convinced there will be no pressure spikes, then I do run into occasionally systems that have no relief valve together with the use of an A10V pump. So yes, that does happen. Okay, be very careful with that and understand what maintenance and adjustments are required. Okay, but most cases that relief valve is there to protect from fast pressure spikes that can occur in the system, and is the faster acting device compared to the pressure compensator. Okay, so I am by no means ever encouraging anyone to remove the relief valve from a system with a pressure compensated pump as an experiment. Always go back to an engineering group for your system before changing anything. All right, we'll move on. There's a few more questions there that came in late, but I think for now we'll move on, and perhaps I'll come back to those a little bit later. So just in case we need to look at a little bit more hardware here, we've been working in abstraction with simulations and what have you, just to remind you of the pieces, or perhaps if you haven't had a lot of exposure to disassembled piston pumps on the inside, which is always possible. I think you're going to recognize some of the pieces here that you saw in our 3D movies, things that you saw in our, this is a pump obviously that's been decommissioned. It's fairly simple and basic, straightforward design where the control, oh, there's that little maximum stroke limiting orifice is fairly large, right? So all of a sudden you get to off stroke and your case drain flow, because this is draining into the case, and all of a sudden the flow rate coming off the case drain line is very high. You've uncovered that port. You've gone as far as you can, and your pump is at the 0 degree stroke angle. Okay. By the way, it's easy to figure out from these three. Here's where the pressure compensator was sitting a few moments ago before I took it off. And if you cover that one with your finger, no, it's this one in the middle here. All of a sudden you could see that that's clearly the one. I'm pumping a little air against my finger there. So that's the passage that is directing fluid into the control piston to de-stroke the pump. And where does it come from? This passage back here, which is monitoring the pump's outlet port. And through a little pressure compensate spool that sits there inside the compensator. Here's our compensator. Make sure that if you ever take a compensator apart, that spool goes back in the right way. Sometimes the bleed orifice in the middle of the spool is meant to be pointed out towards the adjustment, sometimes the other way around. It depends on what internal passages have been set up in there to bleed down the backside of the compensator. So there's the spring. There's the cup washer that the bull-nosed end of our spool rides against. There's our adjustment, okay, and remove that from there earlier. And then, of course, that controller exhaust on the compensator spool dropping down through the hole closest to the connection between the cap and the case, draining inside the case through that passage right there. If I was to stick my screwdriver right down in there, you'd see it in that little hole right there, or to squirt fluid through it with one of our syringes. So that's some basic activity. And if I was adjusting the maximum volume stop, I think you can see that the control piston is extending, so we'll no longer get the 20-degree angle. Perhaps we're only going to get the 10-degree angle unless we turn it back out and allow the pump to be larger. So this literally limits the maximum size, the maximum pumping displacement volume of the piston pump, right? And so what are we supposed to picture? The cylinder barrel, of course, turning there, and right, how do we prevent a lot of leakage from happening between there? Well, what you'll notice is that under the ball washer, underneath the spherical washer, if we look in there, there's 3 tiny little pins holding the retaining ring at a distance. And if I was to squeeze this, you'd see, oh yeah, there's definitely some spring action in there. There's a load spring. There's a load spring inside the cylinder barrel. And as you put the pump back together, assuming you're a pump rebuild person, when you tighten up those cap screws to fasten the cap end of the pump to the body, you find the last few threads, there's some resistance there. You're tensioning the slipper pads, the piston shoes, against the swash plate that you can see inside the pump casing. You see it in there at an angle. Looking in through the case drain, I can see the bias spring in there. So there's all of the basic pieces that we've been talking about. And hope that clarifies some of those. Now, we'll come back to transverse design here in a minute. Maybe just before we move away, let's go and adjust a few pumps and that are of this style with a control piston axially in an axial orientation, meaning in line with the pump shaft, and see what that's all about. Okay, so we've got a Rexroth pump over here. I'm just going to make sure that my flow is all the way open here. I'm pretty sure it is. Okay, and we can see that we're pumping at 1.2 gallons per minute. This one does not have a maximum volume stop, so this one's only going to have pressure compensate. So with lots of flow taking place there right now, I think what you'll notice is that we're not in the right state to adjust the pressure compensator. The pump's outlet line is simply pumping back to tank and right back through the filter, and so it's pretty easy flow path. Not a good state for adjusting the pump's pressure compensator at all. We're measuring the pressure on the pump outlet line. Here it is. We're measuring the pump's pressure on the outlet line with the digital gauge, and oh yes, you might notice that we've got the load sense compensator on there. This is a DFR compensator if you're reading the data sheet for this style of pump. But in this particular case, with the control hose coming out of the DFR style compensator, the valve set to route that compensator right into the pump's outlet pressure, that basically knocks out the flow compensator, the load sense compensator as it's sometimes called at this time. So right now, the way we've got it configured at this very moment, we really only have the single pressure compensator adjustment. Okay, and as I take my trusty 3.5 millimeter, or my 3 millimeter key off to work on this particular adjustment, of course we're not in the right state. We have a free and easy flow path, so if I was to make any changes to the pressure compensate now, we'll find out nothing's happening on my pressure gauge. So I've got to blind out the flow of the pump, and I'll do that by shutting in. Okay, very gradually shut in the pump. Our flow rate drops off to 0, and we can see now that currently our pressure compensate value is around 500 psi, and perhaps it's supposed to be closer to 750. I've already got my jam nut backed off in advance, and so as I make the turn gradually, that's about a quarter turn there. And if I'm supposed to come up to 750, I need to go a little farther, and it's not quite, that wasn't quite half a turn. I overshot. Gotta take my time. I'll come back down, go underneath a little bit, and just give it very small. It wasn't even, it was about a third of a turn to go from 500 to 750 on the pressure compensate, and it's all that complicated. Our pressure compensator has been set, and again the assumption is if you have a relief valve in the system that has already been adjusted. Okay, so that's one example. Let's head over to another unit where I have to get in a little closer, and of course there can be heat involved, so I'll put on some gloves just to be careful. Hydraulic systems can be very hot after a time. I warmed these systems up a little bit today, but they've already cooled down a little bit. And we start with our flow rate. Let's have a look. Yes, we're open to having around 3/4 of a gallon, 0.75, very small flow rates. These are the pump units that typically accompany our training valve boards, and they're just sitting side by side together, and we've created some basic flow loops from pump outlet through a needle valve and then simply back to tank. So a very simple flow loop with some sort of a needle valve so that we can shut in the flow and make adjustments as needed. So right now we don't know what our our maximum system pressure would be, because we've got a nice easy flow path, and our system pressure is certainly quite low, well under 100 psi. So let's find out, see where we are by very slowly closing off. The flow rate will drop and the pressure will come up. As our flow rate drops off to 0, we find out that our pressure compensate at the moment is around 600. Perhaps our pressure compensator is supposed to be closer to 750. So just got to grab the right key and dialing into our pressure. Always check your manuals to find out where your pressure compensator is located. Make very careful adjustments. In this case, to go from 600 to 750 was only about 1/8 of a turn. It's a very small amount of turn on this key to move 150 psi. About 1/4 of a turn was 300 psi change on this particular adjustment. This is a Nachi America pump. You'll see the data sheet for. So there we are back at 600. What did I say? Oh yeah, we wanted to go to 750. Perhaps that's our correct setting. And there it is. And of course, then we would apply the correct torque to the jam nut and lock it so that it doesn't move after we're correctly set. In this case, we can also adjust the maximum volume. Oh, perhaps before we do that, let's have a look at the K-strain flow meter. Okay, should K-strain flow meters be left in place? I don't recommend it. We find that places additional resistance on the K-strain line, and if you don't know what values you're looking for, perhaps not all that useful to leave it there. But in some cases, what it does tell us is that there is an increase in pressure. As you'll see, the K-strain line flow meter is increasing. We're nowhere near 750, our pressure compensate pressure. We're only at about 450 pump outlet pressure. Now 500 pump outlet pressure, 550, 600 psi, and we're up to 0.15 GPMs of flow on the K-strain. And if I shut it in completely, if I shut in the pump's outlet you'll see that there is the highest level of flow on that case drain line that you'll ever see, due to the pressure, due to the clearance between parts, and also due to controller exhaust and the maximum stroke of the control piston. Okay, but if we want to change the maximum flow, we were at 0.7 or something when we were wide open. This is obviously not the time to change maximum flow rate, the maximum volume stop on the pump, because we're currently in the zero flow condition. We need to open the system back up for free and easy flow. Perhaps 0.78 gallons per minute is not correct. Perhaps what we were supposed to be set to is 1 gallon a minute. So which way do I have to turn the adjustment screw? Well, with one of these axial inline control pistons, which are very atypical design, typically to make the pump larger, one needs to turn counterclockwise. This is an adjustment that's lower down on the cap end of the pump. And I'm just going to turn counterclockwise and find out that our pump flow rate, as being measured through a WebTech turbine flow meter, is increasing on the display, 0.91. And I should also mention that there may be a recommended correct temperature for your system to make these changes. I believe I mentioned temperature a moment ago and I didn't finish that, because not so much flow, perhaps a little bit flow will change, but most certainly the pressure compensate value, pressure compensate and maximum flow rate may change a bit as you come to the normal working temperatures. And then of course you must be careful not to get burned by hot hydraulic parts. Okay, so there we are. We have adjusted both the pressure compensate and the flow rate. Our flow rate is now at about 1 gallon a minute. If I shut the flow rate back in, our pressure compensate value should not have changed. That should be about 750. Those two settings are largely separate from each other, independent, as long as you did them at a similar time when the oil was at a nominal level required for making the correct adjustments. All right, that's a couple of adjustments for pressure cutoff or pressure compensate, and also for maximum volume stop. Let's think about another style of pump. It's not uncommon, perhaps just a little less common, but not uncommon to find pumps that have control, the control equipment, the control pistons set across the case in a transverse arrangement, as opposed to the control pistons that were in line with the axis. Oil gears certainly been popular with that over the years. A few other pump manufacturers as well have had various pump controllers where the action for angling the swash plate, the control piston, the pressure compensate functions sit at an angle across the case, and that's just another design to go, possibilities of getting certain kinds of strength and what have you. And of course, I didn't mention earlier this, these pumps can be rated for very different pressures. So this one with a very thick casing and a number of special places with bearing surfaces on the inside. This one is continuous run at 5,000 psi, intermittent up to 5,800, where perhaps the Rexroth A10, the one we've got anyway, about a 3,600 psi nominal pressure, perhaps a bit over 4,000 for intermittent. Whereas the one I was just adjusting a moment ago, the design intention for that one is for it to max out nominal run at around 3,000 psi, and maybe intermittent about 3,500. So they're all similar size, but have different top end pressures, and perhaps some are more heavy duty than others. Okay, this particular pump though, with all of the transverse, we bought it configured with about as many controls as you can ever sort of get all combined all at the same time. So the pressure compensate adjustment is sitting here. This is the adjustment for the maximum cutoff pressure. That's the one we've been talking about the most. And then the maximum volume stop, meaning how large can we allow this pump to be, or do we need to shrink it down from its maximum? That's this adjustment screw over here. And perhaps this one's not quite as common. You might be saying, hey, what's that one sticking out? Well, we deliberately ordered it with this. This is a minimum volume stop, or Q minimum. What happens if you start to turn that one clockwise? With Q minimum, you're literally in a scenario where if you dial it away from its factory setting, dial it clockwise, you're going to set up this pump in such a way that the swash plate, when you go into pressure compensate function, the swash plate will not quite make it to the 0 degree angle. meaning it's going to remain on stroke even once pressure compensate hits. Usually very small amount, if any of that is dialed in. It's not an everyday common value to be dialed in, but we do encounter it on steering pumps, on some mobile equipment where it is desirable to still have some flow definitely coming out of that pump even when fully compensated, which then does definitely require a relief valve, a system relief valve, to be present in parallel for protection, in parallel with the system. Okay, so that's what that is. So that's a minimum volume stop, Q minimum. And then of course, some of you may well know what this adjustment is over here, load sensing. We don't have a line connected to it. On this one, it's just fresh out of the box. That's where load sensing is. And again, come and join us in August for our live broadcast at that time on load sensing. All right, so a transverse-mounted controller. I've got a few little three-dimensional clips to show you on that topic, so let's find those. Okay, so just to give you a bit of a picture there, we're going to start to shut in the flow rate coming out of the outlet. For an oil gear pump here, we're going to shut it in, block off the flow. You can see that our pressure spiked up, so our flow meter showed the drop off in flow and our system pressure spiked all the way up. And watch here, there is a passage from the outlet of the pump that's actually carved right, or drilled right through a very thick pump casing and brought up to the underside of that pump controller. In our 3 dimensions, we lifted the pump controller up from the surface of the pump so we could see the linkage a little bit, so a little bit unrealistic there. This gap does not exist, but it's easier for training. And that flow from the pump's outlet comes to a small passage that's sitting just about here underneath the compensator spool. So there's that adjustment I was just showing you a moment ago that lets you tension the spring for compensator function. Outlet flow or outlet oil pressure also travels past a smaller diameter land on the compensator spool and comes down to the end to act on the end of that spool as well, to push it against spring setting that perhaps you dialed in for what you desired for your maximum system pressure. Okay, so here it is. So right now, I'm going to stop and pause a lot to just catch the moments. So our swash plate angle might be maximum. There's our 0 degree reference, and as that spool opens, that pressure the system outlet pressure made available runs across to our control piston, and linkage in this slot is connected to a rod down below to move our swash plate to the 0 off-stroke condition as you just saw it there. So a lighter spring here, but a control piston that moves and hits against the minimum volume stop, which is dialed out to 0, hopefully, unless you need some. There's our maximum. We'll get to that one in the next movie here, in the next clip. So just looking at it from the side, we can see that the pump is off-stroke, although you really need to see down from the top, and so that's why we showed it with those green lines. We're in the pressure compensate mode. Okay, one last 3-dimensional clip here for us to have a look at. And this one involves... This is what happens here if we're going to adjust the maximum volume of the pump. In other words, make that pump just a little smaller than its maximum possible flow rate. And so what's involved? Well, this is where we bring in an Allen key, a hex key. You saw it shoot in there in the upper right-hand corner of the screen. And of course, as you know, this is done when there's an open flow path for the pump's outlet flow. Pump oil is flowing very freely back to tank with little to no obstruction or pressure loading. And then as we turn that Allen key, we find out that we're just literally changing. You saw the angle of the swash plate there change. I'll just back that up again if you didn't catch it. If you want to look below to see what happens with the swash plate, we're literally limiting the maximum size. Perhaps we've cut the size of the pump in half because maximum flow was perhaps too great for whatever reason. All right. So let's head over to the oil gear pump here with the transverse control, and let's make one more set of adjustments so you can see that taking place. We'll fire up our pump. Obviously, we've got a free and easy flow path right now for oil leaving the pump's outlet. traveling back to tank unrestricted. Because we do have the pressure, because we do also have the load sense control on there, I have a hose on the pump outlet connected right back into the pump control, and it arrives here, and basically using the system pressure to knock out the reaction of load sensing. Come back in August and we'll run this pump with load sensing functions and a variety of different loads on a hydraulic system at that time. So perhaps since we've got a nice open flow path, I'll reverse the order of my action this time. We've got a nice easy open flow path. Perhaps 0.8 gallons per minute is not the correct maximum amount of flow. Perhaps our pump is supposed to be a little bit larger, perhaps closer to 1 gallon per minute. So which way should I go? Should I go clockwise or counterclockwise? Well, as you'll find out, what we need to do to get that pump to be larger is go counterclockwise on the adjustment screw, and here comes our flow. Okay, so we're increasing the maximum flow rate from 0.8 gallons a minute up to 1 gallon per minute, and it was simply a matter of counterclockwise turns on the maximum volume stop. Okay, let's think about what happens here as we need to work on our pressure compensate. And let's watch that K-strain flow meter as well. The K-strain flow meter, what we'll notice as we shut in the pump's flow, got a little ways to go, a little bit oversized needle valve. There it comes. I'm starting to restrict the flow coming out of the pump. And of course, you'll notice the K-strain flow on the increase, down to about 3/4 of a gallon a minute, up to about 600 psi, and our pump is off stroke, and we've revealed our current pressure compensate value is 600 psi. And so now, if it perhaps supposed to be 750 psi, with the jam nuts backed off and loosened, to take my hex key to that pressure compensate control on the opposite side of the pump and turn clockwise to increase the system maximum system pressure, adjusted when flow has been blinded out, up to 750 psi, and that was less than 1/4 of a turn to make that 150 psi change. And again, adjustment should be made at a nominal system operating temperature, but it's not too much more complicated than what you've seen. I'll go back and restore my flow, which takes out system pressure, but our flow comes back. Our K-strain flow, of course, drops right off. And that's the adjustment of a pump with a transverse control, the oil gear in this case. All right, let's go back and see what questions remain from the viewing group today. Thanks for being with us. Yeah, Black Cone says, what's the main application for piston pumps? Well, piston pumps are a fairly good heavy-duty pump. Perhaps gear pumps can take more abuse. So if it's all about abuse, perhaps, and not about energy savings, perhaps one would choose a gear pump, which is common for hoists on haul trucks and all kinds of very heavy-duty applications. But the piston pump gives you the ability to control. It gives you the ability to work with a multiple number of different pressures, depending on what type of controller you've got. There can be torque or horsepower limiting controllers, which can help prevent the engine from stalling if the system's overloaded. There's just so many control options that come with piston pumps. And of course, as we mentioned back near the beginning, energy savings for sure by not pumping over a relief valve any more than absolutely necessary. Thanks. Great question. Andrew's asking, is that Q minimum used to prevent the slight delay in pump stroking up from zero? Yeah, that's an interesting thought, Andrew. Sounds like you've come across a few machines that we have. There are machines out there where that Qmax is moved away from the 0-degree angle to produce a certain servo or control pressure throughout a hydraulic system, where a number of other control valves will need to react when the system is kind of in a low, almost a neutral state. And so yeah, sometimes that Q minimum that you asked about is moved off of 0 just a little bit to make it easy to produce a higher piloting or standby pressure. Yeah, good one.
Andrew also has a comment there. Yeah, okay, great. Oh, yes, very good point. I did not point out that. The electric motor current is at its lowest while the pump is at maximum flow and at zero pressure, yes. But what you would also find out, Andrew, is that when we get to the flow cutoff point closing in the needle valve, the current goes to a very high point, and then just as you close in that needle valve, then all of a sudden the amperage drops off again, because you can maintain high pressure, but if you reduce the flow volume, that does not take as much power from the prime mover as it does when we're at both full volume and full pressure. Nothing requires more horsepower from your prime mover. Very good point for you to bring that up. Nothing requires more power from your prime mover than pumping at high pressure and full flow. If you get rid of one or the other, you can pump at high flow and low pressure and save a lot of horsepower, or you can pump at high pressure, low flow and save a lot of horsepower. But anytime you have your pump at maximum flow rate and at maximum pressure, you're drawing, that's that diagonal line across the square box in that pump efficiency chart we were looking at, that long diagonal line requiring the most amount of power. Great observation, Andrew, thank you. Trigger Tech says, any advantage to a hybrid system that's using variable frequency drive motor and pressure pump? Yeah, well, variable frequency drive electric prime movers being hooked up to fixed displacement pumps is certainly a very common thing now. With electronic controls being what they are, a lot of opportunities are presented to save energy, and so that is becoming a very common package. I'm sure before long in our own training fleet we'll have a fixed displacement pump driven by a variable frequency drive motor. But I think you're asking about a variable frequency drive motor together with a variable displacement pump, a pressure compensated pump. Not as common. That doesn't mean we haven't seen it. We came across one stationary installation a good number of years ago where variable frequency drive motor and load sense piston pumps were used together. And yeah, that became quite a tricky system to create the right control schemes for. It is doable though. Lots of energy savings available. It is doable for some hydraulic system designs. Depends on the application and the usage. Samer asks, how can I, let's see, identify by the valve plate? Whether the pump is a right or a left-hand shaft. Right, well, that's a good question, Samer. So look all over on the pump case. Quite often there will be a directional arrow indicating what direction the shaft is supposed to turn. Sometimes that arrow is just sticking out of the casting in a very nondescript way, and it's got the same color paint as everything else and can be a little hard to see. In fact, I think Instructor Mark here actually took a black Sharpie and darkened in the flow arrow on ours that was just sticking out of the casting, had the same color of, sky blue paint on it, might not have noticed it. On another pump, let's look over here and let's look on this one. Here we see the directional rotation arrow is on the nameplate, so don't let the nameplate get lost or get damaged, so it's there. But Samer, it can also, and almost always does, show up in the many letters and numbers of the model code. So take that model code off the nameplate, get the data sheet, and examine, and that way is one of your best ways to verify. If the inlet and outlet port are different size, as they often are on piston pumps, not always, that can help you, but you also have to know then what the swash plate is doing on the inside, so not necessarily as easy to figure it out that way. Good question. Kier John Alba said, what about a vane type of pump? What about them, right? Aren't they great? Yeah, they could be very high efficiency, compact. A lot of them are made now to be so quiet, so there is a lot of advantages to vane pumps, and perhaps we'll cover those at a future date. And you're right, there can be vane pumps that are pressure compensated and what have you, and controlled, but not as common as the piston pump. So perhaps we'll cover off on vane pumps on a future session. Okay. Can I understand? Let's see. I'm not sure if we'll have too much more time for other questions today. Maybe one last one here. By measuring the K-strain, can we understand the pump condition by K-strain flow? Very tricky subject, and not always easy to do. Yeah, that's just really not an easy one. If you can detect the condition of a pump by its K-strain flow, then quite often you're at 5 seconds to midnight, and many other golden opportunities to measure. The problem with a piston pump through volumetric efficiency testing have gone by. But there have been times when observing K-strain flow and finding out that it was unusual compared to an identical pump sitting right next to it, and that has been a clue for us to dig in on a problem with a pump, where the fastest thing we could do in a service condition in a coffee break between work cycles was to take the smaller hose off the K-strain line and measure and find out that a badly overheating pump had an extremely high value on the K-strain, much higher than the pump data sheet said it should ever be. And so yes, it can be a clue, but not always easy. What I like to see the K-strain flow meter tell me is that the pump has gone off stroke when it's at a certain level, some other things like that. But leaving it there permanently does tend to can cause some problems as well, unless you know how much resistance that K-strain flow meter issues or offers against the resistance of K-strain flow, which should be kept very minimal. Okay. All right, I think we're coming down to the end here today, and if you had additional questions and we didn't get to them, feel free to email them to us, and we'll be glad to continue to take those up with you. info@lunchboxsessions.com, or find me on LinkedIn, Carl Dyke, Industrial Teacher, and send me your questions that way. Thanks for joining us today. Lunchbox Sessions and CD Industrial Group is myself, Carl, Owen, Mark, Nathan, Crystal, Robin, Chris, Ivan, Alex, and Lenore. And also a special mention to Ted, Keelan, Emily, and Grant for all of their contributions throughout the last year. Thanks also to our good friends at fluidpowerworld.com. And our sponsor today, thank you, Oil Gear. And our next live broadcast will be on June the 9th. We'll have a very different type of scenario set up here. It'll look like a bit of a mad science lab, test tubes and what have you, and electronic laser particle counting equipment. So come on back on June 9th to talk about particle contaminants. And we'd love to have you then. Keep up with our schedule and topics at lunchboxsessions.com/live. Thanks to you, the participants, for joining us today. It was great interacting with you. See you soon. This is Carl from lunchboxsessions.com. Bye-bye.